So axis of symmetry, again, is the line that cuts the parabola into two congruent pieces, or two equal parts, or two of the same components, however you want to phrase it. It's really just, as long as it splits it in half, you got the axis of symmetry. All right, so that's my A of S. Vertical lines always take the form of x equals some constant. So x equals, in this case, 1. All right. Now they're also asking us for the vertex where the graph is increasing and decreasing. All right, so we'll just kind of do that all in one shot here. So the vertex is a turning point. So that happens at the x value is 1 because the x value of the vertex coincides with the equation of the axis of symmetry. So 1, -10, the -10 comes from the y value at that location. Right? The vertex is the line or the point of demarcation between increasing, decreasing, decreasing, increasing. So decreasing is the portion of the graph that has a negative slope. Really, if you just kind of think of it as, you know, a graph that you're reading from left to right, the portion of it that's going downhill. All right. So there's a little tail off on the ends here. It's kind of annoying, but the way the Regents does it, and well, really anybody, is they don't always use arrows. So if there are arrows there, then it's obvious that it goes on forever. But if there aren't arrows there, then it may or may not go on forever. It depends on where the curve ends. If it ends at a finite point, then that's where it ends. All right. So here you can see it tails beyond that last point, which is telling us that this is a snapshot of a larger graph. All right. So it's really telling us that the arrows are implied. It's very annoying because you don't want things to be implied. You want it to be explicitly stated, but it's something that we kind of have to live with. All right, so if you want, you can just tuck some arrows on there just for your own benefit, but that's what that means. All right, so I could start formally stating my answer. The equation of the axis of symmetry is x equals 1. All right, if you just write 1, you're not correct. Right, it's got to be x equals 1, all right, because it's saying the equation of the axis of symmetry. Axis of symmetry is a vertical line. Equations have equal signs. There's a lot of reasons why it needs to be x equals 1, not just the number 1. The coordinates of the vertex, 1, -10. Interval for which the graph is increasing, I believe increasing came first, so that would be the green portion of the curve. All right, so that starts at the x value. We're always talking about, when we're stating intervals, unless you're told otherwise, we're talking about the x values. All right, so the x value for which this function starts increasing would be 1. And it's a solid point there. It's not an open circle. There's no, break in the graph or anything like that. All right, does it ever stop increasing? No. So infinity represents never stopping. And so there we have it. All right. Now for decreasing, when does it start decreasing? Negative infinity. So basically, at the beginning of time, it was always decreasing. In the beginning. And then it stopped decreasing once it got to that positive 1. All right. So we talked about this yesterday, but we'll reiterate it again. The standard form of a quadratic. Now this is another one of those Regents things where they call something a standard form, but it's not really the standard form. The standard form that they're talking about is actually the general form. All right, so we're going to include a new field there. I'll take it as a typo. Honestly, I think I took it as a typo last year. I just never made the change. So it's your benefit. So y equals ax squared plus bx plus c. And then we also have the standard form, y equals a times x minus h squared plus k. All right. So there's two ways to come up with the axis of symmetry, and there's two ways to come up with a vertex. One way, I think you'll, honestly, I think when you have a choice between two things, you're generally just going to like one more than the other, or hate one less than the other. All right, so we'll see what you come away with here. All right, for the axis of symmetry, based on the standard form, it would just be very simply x equals h. All right, for the general form, it would be x equals negative b over 2a. For the vertex, from the standard form, very simply, it's hk. When I say it like that, it makes it seem like I'm leading you towards a particular way of doing things. We'll see in a minute. For the vertex, from the general form, it's negative b over 2a, comma, f of negative b over 2a. All right, so we're looking at two distinct ways of handling this. One way is somewhat new, but the formulas aren't too crazy. You know, negative b divided by 2 times a. That's not bad. You take your b value, negate it, and divide by double whatever your a value is. The only thing that would make that challenging, I guess, would be remembering that formula. The other way is related to stuff that we've been working on for like a month. Right? So if you developed any kind of comfort with the completing the square approach, then you already know how to do it using the standard form approach. Right? And fun fact, we already did this. Right? This is back when I was really driving the point home about leading coefficients and things like that with completing the square. So there is an element of familiarity here. So let me just take you through that. So I'll do it with both approaches. So standard form. What we're going to do is, so we start off with the original function, x squared plus 4x minus 7. It's a subtle difference between this approach and what we did in the last unit because it's not equal to 0. Thank you. It's not equal to 0, it's equal to y. So we have to work around that. That's fine. So I'm going to add 7 to both sides, just like I would in the completing the square approach. Then I'm going to actually use completing the square to determine the perfect c value here. All right, so that's, again, taking the b value, cutting it in half, squaring it, dividing by the a value. All right, so what would that number be? 4. All right, I can't just add a 4 to one side of the equation, so I'm going to add it to the other side. So organizationally, it's slightly different, but essentially the same approach. All right, so now I have a y plus 11 is equal to, what's the factored form of x squared plus 4x plus 4? X plus 2 squared. All right. At this point, I've successfully completed the square. That was the objective here. In order to get it into the standard form, I need to have it in that a times x minus h squared plus k format. Very close. The only thing I'm missing is it's not y equals. I have y plus 11, so what should I do? Subtract the 11. So y would be equal to x squared, I'm sorry, x plus 2 squared minus 11. All right, so this is my standard form. In a lot of ways, this is easier than the regular completing the square approach to solve a quadratic, because you don't have to take the square root, which means you don't have to worry about simplifying a square root radical, which means you don't have to worry about forgetting the plus or minus, and you don't have to worry about simplifying a fraction. All right? Once you get it as a binomial squared, you're just moving that other term, the one that's associated with the 11, over to the other side, and you have it. All right? The h value is your axis of symmetry. All right? The k value is your vertex. I think it's easier to identify the vertex first. So my vertex here, now you see that a negative sign is built into our standard form. So what must h be in order for this expression to become an x plus 2? Negative 2. And what must k be in order for this expression to end up with a negative 11? Well, if I replace a k with a positive 11, I'm going to have a positive 11, so negative 11. All right. What most people get from this, or at least look for in this, is a shortcut. Like, all right, I'll just take the opposite of the sign of the number that's on the inside, and I'll keep the sign of the number on the outside. That's fine. But at least try to understand why it works the way it does. Generally, I mean, if you wanted to, it's not ideal that you would have to do this every time, but you have an x minus h and you have an x plus 2. All right, these two things need to be equivalent to one another. All right, so set them equal and solve. Subtract x, well, it's going to cancel on both sides. Negative h equals 2. Divide by negative 1, and you get h equals negative 2. All right, so you can get that. And then on the outside, you'd have a positive k has to be equal to a negative 11. That one should be easier. So therefore, k is equal to negative 11. All right, so you could do the work to get it, but most people are more inclined to look for the shortcut. All right, so I have my vertex, and I have my axis of symmetry, A of s, which is x equals negative 2. All right. This method is almost exclusively relied on stuff that we saw in the last unit and worked on a lot. All right, we spent a lot of time practicing the completing the square approach. All right, so it was like maybe end of the first week, early second week of February, we started with completing the square. All right, so like it really was a lot of time spent on that concept. Right, so you should be very, very familiar with that, to the point where if you're going to default to anything, you'd go with this approach. Now, if you're working with the general form, I didn't really leave myself a ton of room to do it for this problem, so I'll do it for the next one. For the general form, you're plugging values in. It does require you to be in the correct format to begin with, but I guess so does every other problem. So for the general form, you'd identify the A, B, and C values. You don't really need the C value. I'm just going to identify it because I don't want it to feel left out. 3, negative 18, and 1. All right, so my axis of symmetry, x equals negative b over 2a. So negative 18 over 2 times 3. 18 over 6 is equal to 3. All right, so that's my axis of symmetry. To get the vertex, what I have to do is evaluate the original function for that x value. All right, so what I need to do for the vertex here is find y of 3. So I'm going to replace every x value in the original function with a 3, simplify, and when I do that, I should end up with, let me make this a different color, the appropriate y value to make up the vertex. All right, so it's 27 minus, looks like 54, so negative 27 to negative 26. So that would be my vertex. All right. So it's more number crunching, less algebra, more number crunching. But again, if you need to know completing the square, you should at least familiarize yourself with the other approach. Right. And bearing in mind that, the way I operate, I'm going to at some point ask you to do it both ways anyway. So, make it your business to know both. Let me do number 4. Let's see, number 3. Yeah, number 3 and 4 are kind of the same type of problem. 4 is a little bit harder, so I'll do number 4 with you. All right. So I'll do that with the standard form approach. All right. So first move again, get rid of the c value. So it's going to be y minus 5 is equal to negative 3x squared plus 2x. Then I'm going to compute that, again, the perfect value to pop in for c. So take the b value, divide it by 2, square it, divide by the a value. All right. So the b value is 2. Cut it in half, you get a 1. Square it, you also get a 1. Divide by the a value. 1 divided by negative 3 is negative 1/3. So I'm subtracting 1/3 from both sides. Well, adding a negative, right? Same thing. So negative 5 minus 1/3. So negative 16/3 on the left, so y minus 16/3. On the right, just like completing the square from the last unit, you need to factor out whatever the leading coefficient is. So I'm going to pull out that negative 3, and in the process, I'm going to divide each term by that leading coefficient. All right, so what do I get when I do that? Well, the first one should be easy. X squared. Minus 2 over 3x. Plus 1/9. You got it. All right. All the hard work is done because it's just a matter of factoring and moving some stuff around. This is now a perfect square trinomial. That was the whole point of this. So I have y minus 16/3 is equal to negative 3 times some binomial squared. What's that binomial? X minus 1/3. And then all I really need to do to get it into the standard form is swing that 16/3 to the other side. So y equals negative 3 times x minus 1/3 squared plus 16/3. So now I can state my vertex and my axis of symmetry. And I have an equation in standard form which can be used for other things because, this is being used for something. I keep saying this whole thing about the stuff never going away. There's a reason why it's never going away, because we're going to use it down the line for other things.
Wouldn't it just be plus 1/3? Because wouldn't you just do the inverse of the negative?
For this,
No, for the beginning of the equation, because you subtracted 1/3 from both sides. But it's a negative 1/3.
so I'm really adding negative 1/3 to both sides, which is the same.
Okay.
Right?
Yeah,
All right. So my vertex would be what?
1/3, negative 16/3.
Exactamundo. Positive 16/3.
Wait.
So close to exactamundo. Yeah, keep the sign of the thing on the outside.
Oh, yeah.
And so my axis symmetry is x equals what? Just the 1/3. All right. So the benefit of doing this algebraically, because you can get it from a graph in some cases, is that when you see a vertex at 1/3, 16/3, yeah, you can get a 3, negative 26 by counting tick marks on a graph. I don't see how you're getting 1/3, 16/3 from a graph. All right, so the algebraic approach really kind of presents itself here. Juliana, you have a question?
How did you get on the side negative 1/3? Why did you divide by 6? 6 divided by 2?
That's a B.
Oh,
It's the
okay.
completed in a square approach, yeah. You know, just to complete the cycle here, we'll just bang out that last problem there. Maybe I'll do this one both ways. So we'll start with the standard form. So we'll start, some steps you want to be able to get to a point where you're not always, adding this to both sides, just jumping right to it. So y plus 3, I'm going to write as negative 2x squared minus 8x, and then I'll leave the blank. So on the fly, I'm adding 3 to both sides, all right? Just so I don't have to write the plus 3, just create a new line of work for no reason, all right? But again, I'm taking the b value, dividing it by 2, squaring it, then dividing that result by the a value. All right, so what's negative 8 divided by 2? Negative 4 squared
16.
divided by negative 2? Negative 8. So plus negative 8 is the same as minus 8. So on the left side, I'm looking at y minus 5. On the right-hand side, we could pull out that GCF. I have a negative 2 that can come out front. This one's a little easier because it's not going to have the fractions. When I divide everything by negative 2, what's left in the trinomial?
X squared plus 4.
Plus 4x plus 4. Which factors to what? X plus 2 squared. Then I could add the 5, and we're in standard form. So the last one, number 4, was only tricky because it had the fractions. But this one much, much quicker. All right, so the vertex, negative 2, 5, and my axis of symmetry, x equals negative 2. Now, if you wanted to do it with the general form, again, you list out your A, B, and C values. You really don't need the C value for this, but later on in the unit, we're going to be putting all these concepts together along with roots. And one of the techniques that we use to find roots is quadratic formula, which involves using the C value. So why not? Just list it. So negative 2, negative 8, negative 3. The axis of symmetry formula, x equals negative b over 2a. So negative 8 over 2 times negative 2. So we're looking at a positive 8 over negative 4, which is our negative 2, which we got in our axis of symmetry. Right, x equals negative 2. And then the last part of the problem would be to evaluate the original function using that x value. All right, so you could do the math on that, but that's going to end up being a 5, in which case you get your vertex negative 2, 5. All right, so yeah, again, a lot of this course is just really balancing, getting stuff right now in the short term and being prepared for the stuff that comes down the line. This is a strictly numerical approach. There's no algebra here. That's the thing, like manipulation of algebraic expressions involves working with the variables and not making numerical substitutions. So anytime you can do that, you're strengthening your algebraic abilities so that in future courses you're not going to find yourself behind the learning curve. Right? So, you know, you look at this and you say, well, this is extra work. I can get this so much quicker here. Yeah, well, actually, you can get it so much quicker just by typing it into the calculator. Like, you really want to get it quicker. The quickest way to do it, negative 2x squared minus 8x minus 3. Go to my table. There it is. It's symmetric. You're looking for that point of symmetry in your table. Like that's the quickest way to do it. This isn't about the quickest way to do it in all cases. Like when we're learning the process, it's about strengthening your algebraic ability. That's why algebra is in the title of the course. Right? So you got to get to that point. Right? So, you know, really spend the time in class doing the things you hate, because that's probably what you need to know. Right? Okay, so yeah, I know it's like most of the class and, you know, going over examples, but you do have time to practice, not as much time as I would like, but still there is some time. So off you go.